Welcome back. Today we are diving deep, and I mean deep, into the world of high-performance industrial lubricants. We're going to explore the absolutely extreme challenges they face and uncover a groundbreaking nano-additive that's not just changing the game. Oh no, it's starting a full-blown revolution with, get this, microscopic ball bearings.
So, here's our game plan. First, we'll look at the brutal environments that push machinery to its absolute limits. Then, we'll break down what grease is actually made of. After that, we'll introduce this incredible nano solution before putting it head-to-head with the current industry standard. And finally, we'll peek into the future and see what's next.
All right, let's jump right in. To really get why advanced grease is so critical, you have to imagine one of the toughest workplaces on the entire planet for any machine, the oil and gas industry.
I mean, just think about it for a second. You've got scorching heat that literally cooks the grease, causing it to break down. You've got fine desert sand getting into everything, turning that lubricant into something more like a grinding paste. Add the immense pressure from drilling equipment and corrosive salt water, and you've got a perfect storm that can completely destroy multi-million-dollar machinery. This is where the science of lubrication isn't just important, it's absolutely vital.
So what is our first line of defense against this kind of mechanical assault? Well, it's that stuff we all know as grease. But what is it really? What's it actually made of?
Okay, so what's really fascinating here is that grease is, well, mostly just oil, like overwhelmingly oil. But oil by itself, it would just run off and be useless. The real magic, the stuff that gives grease its body and makes it stay put, comes from that small percentage of thickener and that tiny but absolutely crucial slice of additives.
You know, the best way to think about the thickener is like a microscopic sponge. Its entire job is to create this fibrous 3D network that traps and holds onto the base oil. That structure is what stops the oil from just getting squeezed out from between metal parts when they're under intense pressure. It makes sure there's always a film of lubricant right where it's needed most.
And this just shows you that you can't use any old thickener for any job. Nope, engineers choose these very specifically. A lithium complex, it's a great all-rounder. But if your machine is in a wet, marine environment, you need the amazing water resistance of a calcium sulfonate base. For high-speed, high-heat stuff, polyurethane is the star, even if it's not great with moisture. See, it's always a trade-off.
But even when you have the perfect base oil and the perfect thickener, that next level of elite performance, that comes down to the smallest components of all, the additives. So let's move on and see what happens when you introduce a truly next-generation material.
Unlike traditional solid lubricants like graphite, which work by having flat layers that kind of slide over each other, OLCs act like tiny nanoscale ball bearings. They can actually roll between surfaces. This is a complete fundamental shift in how we can fight friction.
And the benefits of this rolling action are just huge. These little nano bearings physically keep the metal surfaces apart, which dramatically increases the load the grease can handle. They help pull heat away from the point of friction, and they form this incredibly tough protective layer on the metal. Engineers call it a tribofilm. Plus, because they're spheres, they stay perfectly suspended in the grease, unlike other additives that can clump up and stop working as well. So what's the bottom line? It's this number, 0.07. That's the friction coefficient we're talking about. Now, to put that into perspective for you, steel sliding on ice is about 0.03. We are talking about getting incredibly close to that level of slickness inside a high-pressure, high-heat machine. This isn't just a tiny improvement, it is a massive leap in efficiency. And that means less wear, less energy used, and longer life for the equipment.
But, how good is it really? To get a true sense of OLC's power, we need to put it up against the long-reigning champion of high-pressure solid lubricants, molybdenite disulfide, which is much better known as MOS2.
This right here gets to the absolute heart of the difference. Like we said, MOS2 works like a deck of cards. Its layers slide really easily over one another. That's how it reduces friction. OLC, on the other hand, it's like a layer of microscopic marbles. It's a totally different and in so many ways more efficient mechanical idea. Rolling versus sliding.
And that different mechanism leads to very different performance, especially when you turn up the heat. In the open air, MOS2 starts to oxidize and just break down at around 400 degrees Celsius. OLC, however, stays perfectly stable all the way up to 700 degrees. For high-temperature industrial jobs, that is a game-changing advantage.
Okay, but what about wear protection? Well, the data really speaks for itself here. In a standard wear test, a pure synthetic oil left a wear scar of 170 microns. Adding old-school graphite made it better, down to 130. But adding just a tiny bit of OLC cut that wear scar down to only 90 microns. That's nearly half the wear of the pure oil. The level of protection is it's on another level.
And the advantages don't just stop at performance. OLC is pure carbon, which makes it much more eco-friendly than Mosi 2, which contains sulfur. It also mixes into oil way better so it won't settle out over time, and it's chemically inert, giving it incredible stability. I mean, in pretty much every single category, it's a huge step forward.
So what does all of this actually mean? For the future of heavy industry, of transportation, of energy, what does a world lubricated by nanobearings really look like?
Well, the takeaways are pretty straightforward, but they're also profound. That superior wear protection means machines last longer, and that cuts down on costs and downtime. Lower friction means less energy is wasted, which improves efficiency and fuel economy. And moving away from sulfur-based additives means a smaller environmental footprint. It really is a win-win-win.